Welcome to EC&M Tech Talks. This is a series of how-to videos where we cover everything from basic theory and electrical equipment and our distribution systems to the installation and maintenance of those systems and the various codes and standards that are related to them. Anyway, this is brought to you by EC&M Magazine. That's ecmweb.com, electrical construction and maintenance. So what you want to do, if you haven't already, you want to go to ecmweb.com. And when you get there, click on the upper left-hand corner, there's a drop-down menu. And that very first item talks about premium content. And so that's what you want to do. You want to go to the premium content section, sign up for it. It's free. And if you do that, you can look at, for instance, today we're going to be talking about variable speed drives. You can find lots of related articles and information on variable speed drives in their system. So anyway, you want to do that, ecmweb.com, Electrical Construction and Maintenance Magazine then. Now, I'm Randy Barnett, and I'm a journeyman electrician by trade, electrical safety compliance professional, worked as an electrical inspector, written textbooks and whatnot in the world of electricity, and this is my passion. So anyway, here I am today, and I'll be your host for this presentation then. So as I mentioned today, we're going to talk about variable speed drives, or maybe it's variable frequency drives, or no, the code calls it adjustable speed drives, but I don't know, maybe it's just an AC drive. Well, this one is, but I could get a DC drive. Maybe we just ought to call it the drive, huh? Well, what I'm getting at, terminology, there's a lot of different terms when it comes to these devices. And this one I have in my hand is obviously pretty small. It's for a relatively small motor. It'll operate a three-phase motor. And I don't know, we could look on the nameplate and see, it'll tell us. It puts out 1.5 continuous amps, 0 to 240 hertz, three-phase power then. Okay? And so anyway, 1.5 continuous amps. Now, I can use this on the appropriate size motor to operate that and then vary the speed of it. Now, if we take a look at the drive, and we will, this, we've got some controls up here in the front. I've got some start and stop. Let me get a little closer for you. I've got a reverse push button where I can reverse the rotation of the motor just by pushing that one button. Then up above, I've got some various control buttons that I can select and program the drive, and I can read my LED readout up above and figure out what the heck I'm doing then. So in other words, I can use the drive to maintain constant torque or constant speed on the motor. I may want to, when I shut this motor off, I may want it to coast down and stop rotating in 7 seconds, not 15 or 20 or 3, but 7 seconds, okay? I may want to start the motor and gradually bring it up to speed. I can do all these type things with this variable frequency drive, I guess we'll call it. So these drives all started to come about way back in the 1950s, late 1950s probably. And our first drives were just for DC motors. They would control and operate DC motors. Technology began to change, obviously, and we started to use them, or they developed them for AC motors as well. And they were high maintenance items. I can remember back when I first learned to work on drives way back in the 1970s. For example, we had a drive that we would use. This was in the submarine service in the Navy. And we would take in fresh water and convert it, or excuse me, take in seawater and convert it into fresh water and then pump the brine overboard. That pump to pump the brine back overboard was driven by a AC motor with a variable speed drive then. And that variable speed drive was driven by silicon controlled rectifiers, SCR. And that tells you right there, we're going to have some problems with an older style drive like that because of temperature. As we would go up near the surface and try and pump that brine overboard, you didn't need much pressure to do that. And so the motor would slow down. The voltage would decrease to the motor to slow the motor down. But the motor continued to draw too much current. And what would happen is you would end up having to get out your 1 inch or 1.25 inch, I don't remember, whatever it was, and go in there and shut down and that drive and replace those big silicon controlled rectifiers in because they would burn up. Today, we don't have that problem. Modern drives today use insulated gate bipolar transistors, IGBTs, in order to vary the speed of the motor. Lots of applications for variable speed drives, variable frequency drives, as we'll see. So lots of applications for these drives. Maybe we have a conveyor system that we want to maintain a certain speed and torque, in other words, on that conveyor belt. Maybe a very common application is in our ventilation systems, right? Rather than open and close a damper to vary the flow into a room, why not use a variable speed drive on that fan to control the speed of the fan? A lot more energy efficient to do that. So now we see a lot of variable speed drives like this, and possibly a little bigger, certainly, inside of our HVAC equipment. Lots of applications. I've seen, in fact, I've worked on drives, 4160 volt, 5,000 horsepower ball mill motors. That drive is bigger than the wall that's back here behind me and probably 7 foot tall. But they all work the same way. In fact, so that we can get a little bit of a handle on how these drives operate and how we install them, let's go ahead and take a look at just a basic kind of a one-line block diagram of how drives operate then. So let's put this up. And now we're looking at just a basic diagram of a variable speed drive or variable frequency drive. In fact, I usually refer to it as a VFD or drive, okay? So it's really pretty much whatever you want to call it. Anyway, we're going to take in three-phase power over here on the left. So three-phase power is going to go into our drive. So the drive is shown inside of the dashed lines then. Okay? And so we take the incoming three-phase power, and we like to use three-phase once again because it's more efficient. And the first thing that happens is it goes into a converter. A converter changes AC into DC. And so that's going to provide an output to something we call the DC bus right here. Now, the DC bus is the converter, by the way, the rectifier assembly inside the converter. And there are different types of rectifier assemblies depending. But anyway, what that rectifier assembly is going to do is going to produce a DC voltage, not at the RMS value of the AC, but at the peak value up here at the top. Well, if you remember your basic electricity, if I take the RMS value, for instance, 480 volts, and then I multiply that RMS value times 1.414, that gives me the peak value. So on a 480 volt system, that DC bus charges up to about, well, almost 700 volts. I think it works out to like 686 volts if you actually had 480 volts RMS in. So anyway, what I'm going to do now, I'm going to take and I'm going to feed that DC bus voltage into the inverter section. And what inverters do for a living is they take direct current and they invert it into alternating current. Except in this case, I'm going to use my controls on the drive, those little buttons I showed you up on the top, and I can program in and tell this drive how many pulses per second I want in both the positive and negative directions. So I can vary the output pulses that you see over here on the right going to the motor. I vary the height or the voltage on those pulses, and I also vary the width of those pulses. So we call it pulse width modulation. In fact, the voltage will change in proportion to the width of the pulses. So as you can see, for instance, it's kind of sort of like a sine wave. I'll have a whole series of little pulses in the positive direction, and then pulses in the negative direction of the motor, and then pulses again in the positive direction, many pulses, and then many pulses in the negative direction again. And the result is it's sort of like, kind of like a sine wave, okay, going into the motor, except it's a series of either positive or negative pulses in. So we call that pulse width modulation. So that is how our AC drives work then. And that's by far and away the most popular thing out there on the market today. If you and I had a nickel for every AC variable frequency drive out there, I don't think we would have to worry too much about retirement. We'd be in great shape. Huh? So there's lots of them out there and lots of applications. Now, next thing let's do then Let's take a little bit closer look at the drive itself, and then we'll get into the requirements for the installation on these drives and the maintenance requirements. So anyway, as I pointed out on my drive, I have, oh, and by the way, the other drive I have over here, I'll just point out real quick, this is a nice little drive. I like this. I use this in my shop because it takes in, I can put in 120 volts in on this drive on the top side, and I can get 3-phase 240 volts out. So that's pretty handy for all my little play toys here in my shop. Now, let's take a look at a typical drive then. I've got the controls, as we mentioned, on the front, and I'm going to pull the bottom section off so we can see where we connect to this drive. The first cover I pull off, and I have some terminals up here, and these are for all of my controls. So if I want to put a limit switch in, if I'm using my drive for something for travel, and when I get to a certain travel, I want to slow the motor down and stop it, I can provide that, maybe stop it, like I say, in that 7 seconds or 10 seconds or whatever. I can do that with these functions. I can also use an analog input, a 4 to 20 milliamp signal or 0 to 5 volts, depending on my drive. And I can then, you know, as my tank is filling up, perhaps I want to start to slow my pump down as my tank gets nearly full and so forth. So lots of different controls. Let's pull off this bottom section, and we'll take a look at the main power. So now down here on the bottom left, I've got 3 terminals. This is L1, L2, and L3. So this is where on this drive, it's a 240 volt 3-phase drive. So I can take in 3-phase power on this drive, line 1, line 2, and line 3. And then it goes into the internals of the drive where it gets converted into DC, feeds the DC bus. And then based on the control section up here, the inverter will send out pulses from these bottom 3 terminals on the right over here. That's T1, T2, and T3. And those are the 3 terminals in that go out to my motor. I also have 2, if you can barely see them down here, 2 terminals for grounding, green terminal screws. Then I've got on this particular drive, I have 2 more terminals over here on the bottom left, and that is for regenerative braking. So as you know, when I de-energize a AC motor, it turns into a generator and provides current that flows back into the system. Well, I can take that current and feed it into a big resistor, which will act like a dynamic brake, or will be a dynamic brake, and I can use it to control or stop my motor as quickly as I need to then. So anyway, different functions on the drive as we need it. Okay? And as far as maintenance requirements on my drive, not like they used to be. Those old drives that I was telling you about, that they were called voltage source and current source inverter drives and things like that. Those older drives required quite a bit of maintenance because there were a lot of temperature problems. They were generally in larger enclosures. There may be a fan associated with the drive and so forth, even though this one does have a small fan on the bottom down here for cooling. But there was a lot of maintenance on those older drives. Today's drives really are fairly maintenance free. In fact, I hate to admit it, but a lot of these drives are just commodity type items where if they fail, we don't troubleshoot the drive itself, or we check the program in it certainly. But if we have a problem with the internals of the drive, we often just replace the drive, or depending on the size of the drive, send it back for repair. So anyway, also, by the way, there's a communication port right here on the drive. And turn it up so you can see in there. So the communication ports, different methods of communication. I can certainly plug in my PLC. I can communicate with a PLC in order to talk with my drive and give it commands based on what else is happening in my system and so forth. The Ethernet, as far as talking with drives, is very common now. We see a lot of that in manufacturing processes and so on. So anyway, back to maintenance then. As far as maintenance, you follow your manufacturer's instructions then. These drives have many built-in protective features. We keep the fans clean on the bottom. We make sure we have adequate airflow. We watch ambient temperature. Larger drives, we can open them up and we can, follow manufacturer's instructions to actually physically clean the drive itself and so forth. But other than operational checks on the drive, there's not a lot of maintenance associated with many of our variable speed drives today. As far as troubleshooting, quite often the problem is not with the drive. It may be with the communication system or even the motor itself. So obviously you have to trace that out and do some troubleshooting there. Okay. As far as the drive, the screens on the drive now, we can go through and check all the parameters we need to. You have to have the manufacturer's manual for this drive or whatever drive you're working on, or else you're going nowhere with it, okay? Because all you're going to get is numbers up here. And you have to program in the different numbers. You have to know what I don't know what D1 is or something like that. You need to look in your manual and find out, oh, maybe that's for over voltage protection or whatever it is, right? You'll get alarms when the drive shuts down. So you have to come up and interpret that alarm and find out what's wrong with it. In fact, on the side of this drive, there's a little cheat sheet that gives you for fault codes. I'll just read a couple of them to you. Some of the faults associated with this particular drive. They're FO2, FO3, FO4 on to FO122 or F122, I'm sorry. And covers things like auxiliary input fault, power loss fault, motor stalled, motor overload, heat sink over temperature, ground fault, analog in loss, phase to, phases T1, T2, and T3 going to the motor could have a ground short on them, drive overload, power unit fault, and communication loss, and I/O board failed. That's probably not a good one, huh? Okay. So anyway, lots of information associated with each drive you have to be aware of. Okay. So that's kind of in a nutshell how our drive works and typical applications for us. Let's now take a look at some of the installation requirements on these drives. So as always, whenever I get into installation requirements, I'm going to go to the National Electrical Code. I'm going to use the NEC 2020 because it is our latest. And we're going to find, I could go in the back and I could look up adjustable drive systems, I suppose, in the index, but it's going to take me to Article 430. So I'm in Article 430, and there are several different parts to Article 430. So Article 430 is on motors, motor circuits, and controllers. And Part 10 is on adjustable speed drive systems. So that's why I am on Part 10. So I'm going to take you through the sections on Part 10 of Article 430, and we're going to hit the highlights for the installation of these drives. Now, one of the first things it tells me in Part 10 is that everything else applies. All those first 9 parts for Article 430 on motors and controllers, it all applies unless there's something in here in Part 10 that changes it a little. Okay, so we'll take a look at that. So that's the first key part. This is not a separate standalone section by any means, right? This is Part 10 of Article 430 on adjustable speed drive systems is what the NEC calls it. So Section 430.122 is on conductors. So if I'm going to size the conductors that come in, let's say my 3 480 volt conductors come in and supply my 3 480 volt terminals on my drive. So that's L1, L2, and L3. Should be no surprise to you. I'm going to size these conductors based on 125%. If you do a lot of motor calculations, you know where that number comes from. But anyway, 125% of the full load current rating, not of the motor down here, but of the drive. So I have to look and see, well, I said AC incoming amps is 1.8 amps, 1.8. So I would have to take 125% of 1.8, and that's how I would have to go to my table 31016 conductors, adjust for temperature and number of conductors in a raceway and so forth, and size my conductors coming into this drive then. Obviously, a lot of your drives, bigger applications are going to have much larger conductor sizes. So anyway, 125% of the drive, not of the motor. Why? Because the drive, the power supply system back here, my feeder or branch circuit to this drive never sees the motor, does it? All it sees is a piece of electronic equipment. So it sees electronics. Now, Subsection B of 430.122 then talks about sizing the conductors off of T1, T2, and T3 over here that go out to the motor. Well, I'm going to size those conductors based on the full load current of the motor. In fact, I just like I do for other motors, I'm not going to look at the nameplate on the motor. I'm going to go back in the back of the book, or excuse me, in the back of Article 430, around Article Section 430.250, and there are some tables. So I'm going to look in the tables for the AC motors and three-phase motors and determine based on that horsepower motor, 460 volt motor, how many amps it draws. And I'm going to take 125% of that value to size these conductors to go out to my motor. Once again, make adjustment and corrections as needed, right? So that's how I size my conductors then going to the motor. Now there's some other specific information in 430.122 that you might want to take a look at. Bypass device. This motor, this particular drive does not. Some of your larger drives, you will have a bypass switch on it that you can bypass the drive and just run the motor at full speed. In that case, yeah, you're still going to use 125% of the full load current for the motor to go from that bypass switch on out to the motor then, okay? Because you're directly feeding that motor with that AC power if you have the bypass. So that way you can take the drive out of service and just run the motor at full speed on the bypass. And 430.124 is on overload protection. And it says you've got to have overload protection, right? So overload, where the motor draws a little too much more current than what it's rated for. And that's going to cause me problems. I can overheat the motor, and I don't want to overheat the motor. Rather than, I don't want to put any type of overload device downstream of my variable speed drive, okay? What I'm going to do is rely on the drive to provide me overload protection. So we can program into the drive what we want for overload protection on our motor. So that's pretty handy. That's pretty nice. Now, if I have the bypass device, if I have a bypass, which is really just a disconnect that takes the drive portion out of the circuit and puts the direct 480 volts three-phase AC into the motor, then on that disconnect bypass, I would have to have some type of overload protection for the motor. But normally it would not be in the circuit unless I was on bypass them. Now, let's see what the next section is. There's overload protection, 430.124. 430.126 is on over temperature protection. In most cases, that's probably not going to apply. It has to do specifically when I'm operating a motor at greater than its nameplate to meet the speed applications of the system and so forth. So it's pretty specific, but take a look at it. It certainly may apply to you in some cases then. 430.128 talks about disconnecting means. So it allows me to, because we have to have a disconnect for the motor, right? It has to be within 50 foot of the motor and within sight from, which means visible and within 50 feet from the motor. Now, I can use the circuit, my branch circuit or feeder that's supplying my drive for that disconnect for the motor, even though the electronic drive is in the middle of that. In some cases, we will take and come off the drive and we can install a disconnect. Got to be real careful if we do that. It's permitted by the code. We're allowed to do that. But if we do that and we open up that disconnect while the motor's running, we're going to probably destroy the drive. So we don't want to do that. So we're going to have an auxiliary contact in that disconnect between the drive and the motor then, so that it will first shut off the drive and then the main contacts will open up and keep the motor de-energized. And so that might be handy application where I need a lockout tagout device installed within inside of my motor. So disconnecting means then. And then 430.130, branch circuit, ground fault, short circuit protection for power conversion equipment. This is power conversion equipment, isn't it? Okay. And I follow my rules for overcurrent protection then. There are specifics in there that you can read through, but pretty straightforward. And then finally, 430.131, several motors or loads on one branch circuit, including power conversion equipment. Okay? So it gives me the specifics and actually primarily refers me back to 430.53, where you'll find more information on that. Okay? And so that is it as far as time-wise on today's presentation. Remember, this is brought to you by EC&M Magazine, Electrical Construction and Maintenance Magazine. They are part of the portfolio of Endeavor Business Publications. Make sure that you go to the ecmweb.com, sign up for that premium content. The main thing is, no matter what you do with drives or anything else in your electrical system, make sure that you work safely. Want to make sure you're here for the next Tech Talk, okay? So thanks again. We'll see you at the next Tech Talk.